All right, boys and girls, in this video, we're going to actually verify some identities. In class, we just simplified some trigonometric expressions, which is definitely the beginning of verifying identities. But in this video, we're going to actually work our way through some example problems. Firstly, let's define identity. Here I've got a very textbook definition. Two functions, f and g, are identical if f of x equals g of x for every x in both functions. All right, so what does that mean, Mrs. Burwell? Well, that means that if I'm looking at a statement where I've got a left-hand statement equals the right-hand statement, that means that the left and the right statements are interchangeable. And I could take the left statement and use some substitutions and use some legal algebra and make it look exactly like the right-hand statement. Or I could take the right-hand statement with some substitutions and some legal algebra and make it look exactly like the right-hand statement. So the substitutions we're going to use are going to come from the identities that we've already listed in class. Our reciprocal, quotient, Pythagorean identities, the even-odd identities, and then our double angle formulas or double angle substitutions. So let's get started and see what we have here. All right, at the top of the back of this page, I've got a couple of general rules listed. They are general because each problem is different. Not every rule applies to every problem. But we do have a couple that do apply to every problem, and that would be the first two. Firstly, we want to manipulate the side. We want to change the side with the most complicated expression. It could be on the left, it could be on the right. That's really up to your judgment, and of course, the more you do, the more comfortable you'll become making that decision. The second thing we want to make sure we do is we make no changes to the other side. Your job is to prove that one side is exactly the other. You're going to manipulate it, change it, make substitutions, do some algebra, and it's going to wind up looking exactly like the other side. So these two apply to every problem. So let's put an asterisk by those because those apply to every problem. Rule number 3 applies to many of them. Writing all the trig ratios in terms of sine and cosine usually helps. That's also a positive, a good thing to think about. If we look at our reciprocal and quotient identities, we can see that through those we can write anything in terms of sine and cosine, and so we want to keep that in mind as well. All right, so let's get started. We'll go back up to 4 and 5 when we encounter those. All right, I've got the secant of x times the sine of x equal the tangent of x. Well, I think we can agree that the left side is much more complicated than the right, so I'm going to work on the left side. I'm going to rewrite secant using a reciprocal identity as 1 over cosine. All right, notice I write what it equals every time, and that's not optional. You have to do that. All right, now let's multiply these two terms together and have the sine of x over the cosine of x, which I know you know is tangent. So this is a pretty simple identity. So we wind up with the statement that tangent x equals tangent x. Ta-da, we're done with that one. All right, let's look at problem 2. I think there we can also agree that the left side is far more complicated than the right side. So let's see what we can do there. Firstly, I hope we recognize that sine times secant is the product of reciprocals. We know that secant x equals 1 over sine x, and when you multiply reciprocals, you get the number 1. Doesn't matter whether you're working with trig or with numbers, doesn't matter. So now I have 1 minus cosine squared x equals sine squared x, and heavens, we should recognize that as a Pythagorean identity that we've been using quite a bit in our solving trigonometric functions. All right, let's look at number 3. Number 3, we've got 1 minus cosine squared x times 1 plus cotangent squared x. I'm actually going to do this one 2 ways, but there's more than 2 ways to do this, and perhaps that's probably one of the frustrating things about this for some students is that there's more than one way to get the right answer. All right, 1 minus cosine squared x I recognize as a Pythagorean identity, and that equals sine squared x. Well, I also recognize 1 plus cotangent squared x as another Pythagorean identity. It equals cosecant squared x. Well, hopefully you see now that we've got a product of reciprocals. It doesn't matter whether they're squared or not, and so that is definitely 1 equals 1. All right, that was definitely the shortest way to get there. Let's see if we can see another way. A little longer, but equally as effective. I'm still going to substitute for 1 minus cosine squared x. I'm going to substitute sine squared x. And then in the parentheses here, I'm going to change cotangent squared x to cosine squared x over sine squared x. All right, so now I've got one term times two terms. Let's distribute. So sine squared x times 1 is sine squared x. Sine squared x, remember it's over a denominator of 1, times this fraction here means the sine squared x are eliminated, right? Leaving me with just cosine squared x. And there we go. There's our basic Pythagorean identity. There's probably one or two other ways to solve that problem, but I won't go over those in this video. Maybe you can offer that in class when we come back together. All right, there's a typo in number 2, so please make that change. This sign should be a subtraction sign in front of cotangent squared negative x. All right, this uses the even-odd properties. So we see that we've got a negative x in an odd property. What happens when that occurs? Well, it makes the entire function negative. So let's rewrite this. So that's negative cotangent squared x. And I've got 1 minus a negative. Well, that's 1 plus cotangent squared x. And that is a Pythagorean identity. All right, all these seem pretty simple, and so far they have been. Now let's look at some more interesting problems. All right, I've got secant x subtract tangent x, and it equals to cosine x over 1 plus sine x. One thing I want you to note, I have two terms on the left, I have one term on the right. So my goal is going to be to make two terms be one term. I see the left side is more complicated, so that's the side I'm going to work on. Let's follow rule number 3. It's always a good idea to get things in terms of sine and cosine. So we'll write this as 1 over cosine x, and we'll write this as sine over cosine. Notice I write what it is to equal each time. All right, notice the common denominator. So I'm going to write this as one term. All right, I've accomplished my objective, at least that objective. Now I have one term on each side. And now I'm kind of stuck. Almost looks like I've got reciprocals of each other on either side of the equal marks, but I really don't, because I've got a 1 minus sine x in the numerator on the left and a 1 plus sine x in the denominator on the right. All right, I want 1 plus sine x to be a denominator. Let's look up to one of the other rules here. All right, we did actually apply rule 4. We got a common denominator. That wasn't too hard. But now we're at rule 5, right here, rule 5. If there's a quotient fraction on one side of the identity, introduce that denominator to the other side by multiplying by the equivalent of 1. So that's exactly what we're going to do here. All right, so I'm going to multiply the left side by 1 plus sine x over 1 plus sine x. I can do that. I can multiply any time by the number 1. All right, so what do I have there? I've got 1 plus sine x times 1 minus sine x all over 1 plus sine x times cosine x, and that equals cosine x over 1 plus sine x. All right, here we go. I'm going to actually multiply these two. These are a difference of perfect squares. So I've got 1 minus sine squared x here. Notice I did not multiply in the denominator, and I don't want to because I want to see the 1 plus sine x. That's the denominator I want. All right, I really would like a cosine in the numerator. 1 minus sine squared x is, ta-da, cosine squared x. And I think you can see where this is going to go now. Now that I've made that Pythagorean substitution, I can do some reducing, and I have exactly what I set out to prove, simply by introducing that denominator into the problem. All right, and we are finished with that. Okay, let's look at the final problem. We've got two things. I'm sorry, we don't have two things. We have a product, which is one thing, and we want to move it into two things. We've got two terms, secant x plus cosecant x plus secant x. All right, so what could we do there? Well, I think the left side again appears to be more complicated. So I'm actually going to, you could FOIL or distribute as you want to, but before you do that, I'm going to change things into terms of sine and cosine. Because that means this is going to become sine x over cosine x plus cosine x over sine x. All right, at that point, you could FOIL if you wanted to. But I'm going to get a common denominator here in this term. All right, so what am I going to do? Let's see, my denominator is going to be cosine x times the sine of x. I'm not going to do anything to this. All right, if I want the denominator to be cosine x times the sine of x, I need to multiply the first fraction by sine over sine, so that will become sine squared x. Did I lose anybody? I'm going to multiply this fraction by sine x over sine x. Then I've got to multiply the second fraction by cosine x over cosine x. So that means that this will now become cosine squared x. Well, what does sine squared x plus cosine squared x equal? It equals 1. Okay, now we're going to distribute. Now let's distribute. This is one term. So this times cosine is 1 over sine. Plus this times sine. The sines are eliminated. Firstly, the cosines were eliminated. Remember, this is all over 1. Now the sines are going to be eliminated. So I'm going to get 1 over cosine. And I think you can see where this is going. Well, 1 over sine is cosecant. 1 over cosine is secant. And that is exactly what we were to prove. All right, you have some problems in your textbook, just a couple for you to try on your own. So give those good attention, and I'll see you in class.